Hi all, and welcome to the webinar with me, Daniel. Just want to double check to see if the audio is fine on the side, and if there is any questions, please let me know in the chat box. So before we start, just want to double check if you can hear me clearly. You can see the screen. If one of you could just type in the chat box, that will be great. Then I know it's all working, and then we can start. Perfect. All right. Okay, cool. So thank you very much for that. I'm going to start the webinar. So today's webinar is based on Fusion 360, the simulation environment on it. We're going to be looking at some of the factors of safety that we generally look at when we're doing a simulation. And we'll cover some differences in simulations that we get and what's available to us. But before we start, I just want to take you through who is Baker Baynes. So Baker Baynes has evolved over the past 5 years from being an Autodesk reseller to a consulting company. And we set out to solve customer problems through digital transformation, helping them design and make a better world. In doing so, we offer various business process improvements, consulting services, survey design and hardware, and consulting assessments, software design consulting, and top it off with that, we support a blended learning approach, which we believe our customers can and should be doing and working with. This is supported, of course, by CADLearning, the online platform. Very, very useful for these times that we're in at the moment. The remote working and working from home. CADLearning is something which is being used quite a lot. And of course, there's also classroom training and e-learning that we do. So online training, hosting of training as well. Some of the industries that we serve. The build environment. So we have consulting consultants that serve the following industries. So it's the build environment, the manufacturing, the civil, energy, as well as mining. So the mining industry as well, process plant and mining. So some of the learning objectives for today, you'll find that we're looking at the simulation environment of it. So you'd learn about Fusion 360 simulation, so understand what the simulation environment does, how it works, what's available to you in it. There's a little demo to show you a couple of how it works and how you could have a look and see what's available to you. We're going to be concentrating on non-linear and some static or linear stress in the Fusion 360 environment or the simulation environment. The idea behind this is for you to understand that Fusion 360 has these capabilities that you can explore and use. And we'll also look at the factors of safety and what they mean, just a bit of theory on that. And of course, we'll explore navigate the results. So it's more or less based on the Fusion simulation environment. So just to move forward. So why do we use simulation? Very simply, simulation helps us validate our design decisions before we could actually make a physical prototype, right? It helps us answer those what if questions. So what if I add a bit of load here, what would happen? Or if we have to make this a bit lighter, what would happen? Also predicts the performance, so helps us predict performance of our design. To see how our design will function and work and how it will perform in the real world, right? But also simulation enables critical engineering decisions to be made earlier in the design process. And by having this, we are able to actually, again, predict, have these what if scenarios and also see how the design will perform. But also before we go out and make a physical prototype, we can simulate it to see digitally what it'll do and how it would work, right? So just a quick saying there, simulation is a great way to understand how your designs will perform in the real world condition before they go into production. All right, that's basically what it is. If we look at the simulation environment in Fusion 360, we see that it is powered by the Autodesk Nastran solver. Now, interesting thing to note here, the users that work off the collection, you have access to the Nastran solver or the Nastran Inventor Nastran, Nastran in CAD. And that plugs in nicely with Inventor. But for the Fusion users, which is also in the collections as well, the product design and manufacturing collection, you find that you have access to the Nastran solver powered by Fusion in the Fusion 360 application itself. And there's various types of simulations that could be handled in here. Linear static stress is one modal, so for frequency, vibrations, thermal analysis, thermal stress, structural buckling, shape optimization, a very nice shape optimization, trying to make your designs a bit lighter. It's very helpful. Linear structural buckling, non-linear static stress, as well as event simulation, so drop tests. So if something falls off, or if it's dropped from a specific height, what would happen? So that could be easily handled inside of the Fusion 360 simulation workspace. Now, what's very nice and very cool about this is you've got access to the cloud solve. With the cloud solve, you could do your simulation solving in the cloud, so you free up the workspace on your machine and you don't use any extra resources to do this. This is a simplified workspace, so basically you can simplify the part before sending it to simulation. This is something that we try and practice often, because you find that when a model has a lot of intricate curves or fillets and chamfers which are not really affecting the stress or the outcome of the results, best to simplify them before you take them into the simulation environment. And also the compare workspace. So simulation as a compare, you can compare between different simulations that has been done to see what the differences were in them. So very comprehensive, very nice, and you'll see it's very easy to actually work. Today's example, we're going to be looking at linear static stress as well as non-linear static stress for the examples today, and we'll look at the factors of safety from that to see how if we're in the design criteria, we've met the requirements for the design, and we can have a look at it from there. So, quick question, what is FEA? Just to jump into it, because this is part of the FEA analysis side of it. Finite element analysis, sometimes called FEA or FEM, finite element method, is a computational based method of simulating, analyzing the behavior of engineering structures and components under a variety of conditions. So we put some conditions, some loading, some forces on it. We put some fixed points if there's any context, and we tell the software to run an analysis. What it does, it breaks down the part into multiple elements and nodes. So elements that will be there, very tiny, that's our mesh, and depending on the size that we define it to, it breaks it down into very, very tiny little elements, and it works and calculates each one from there. And there's two types that we could look at, and as we mentioned, we've got static stress and non-linear static stress that we'll be looking at today in our example. Looking at the simulation types that we have available in Fusion itself, we've got static stress, we've got modal frequency, we've got thermal stress, structural buckling, non-linear static stress, event simulation, and of course shape optimization. Now, if we look at static stress itself, we jump straight in. You'll find that simulation types here, a little graph here that explains it slightly with a bit of a formula on it. So static stress material is linear, so loads are applied slowly and steadily on it, and structural deformations are pretty small. Then we would use a static analysis of static stress. Right? Whenever I look at static stress or look at nonlinear, one of the things that comes to mind is the principle of Hooke's law, right? Which states within the limit of elasticity, stress induced in the solid due to some external forces. So the force that's applied is always proportional with the strain. So in other words, the force causing stress in a solid is directly proportional to the solid's deformation, right? It always comes to the back of mind when I think about these types of stresses. And if we look at an example here, this is an aircraft elevator bracket, right? So the GKN bracket. And the design criteria on this is the material that we're going to use. It's a TI6AI4V, which is an alpha beta titanium alloy, right? It's high strength to weight ratio. It has excellent corrosion resistance. It's one of the most common used titanium alloys that's applied in a wide range of applications. For example, like in this case, and the aerospace, so an aircraft elevator bracket, but also used in biomedical or biomechanical applications, right? So it is quite a specialized bit of material that's been used, right? In this example, the minimum factors of safety here is 1.2, so that's a minimum we could go, and the maximum displacement is going to be just over 0.5 millimeter, so 0.55 millimeters that we're going to work off. So let's run this through some simulation and see what the results look like. So very simple. We come into Fusion, go into simulation environment, pick up the static stress, and you see it gives you a nice option to choose. When you start it, you've got the great options to go through it. It reads from left to right, like most simulation packages. With Autodesk, what we're doing is we're actually simplifying this a bit. So we removed all the extra bits that we don't need. We can choose the material type that we're going to work off, right? We can look at the Fusion library, or if there's a favorite library that you've got, or a custom library of materials, you can see it there. We've picked that up. We're going to add in some of our constraints. So constraints allow us to fix it. So how is it fixed, and where's the fixed point going to be? And these holes are representing a fixed area as well as the back. So this shows us the area that it has been fixed to or mounted, right? We can add that. Next bit is we're going to add in a force that's acting on this. So there's going to be a force or a load that's acting on this. We're going to say hydrostatic pressure, right? Or it's a structural load that's on it. It's acting in those points there, and we're going to just fix it so it's correct. So it's kind of remote forces, so we'll have to check on the X, Y, and Z where they are. So the force X, force Y, force Z planes, where they're acting on it, and we're happy with that. It's okay. Contacts are very, very important. So we could tell it if it's fully constrained, if it's allowed to move flexible by just choosing the colors in there. Again, I'll solve locally or on the cloud, and let's choose the cloud study, and you can see it is quite quick. We get the results back. We can see in this case, if we look at the stress itself, what's going on. What's very nice is on the top to the right hand side, you'll find that a little dialog box opens up. This gives us a bit of information on the design that we've got. So it gives us basically an indication that we are in design, we're meeting the design criteria. It's not going to break with the current analysis criteria that's inputted or given. It's going to withstand it. Now it is a bit exaggerated, as you can see, but what it does, it probes the maximum stress points of the model that's there. So in here, the maximum is 136.2 megapascals, and we can also actually see with the colors the area of stress where it's acting the most. Now, there's something to be careful of here called stress singularities, which we'll talk about a little bit later. That could it could actually displace our results as we're looking at it. So we look at the results on it. If you look at the safety factor itself, the maximum safety factor is 15. The minimum was 6.42. So design criteria, the safety factor, the minimum we could have went to was 1.2. So as you can see here, we're way above that. So that's perfectly fine. We meet that criteria. If you look at the stress side of it, so the von Mises stress, okay, we can see here it's 120.1 megapascals at the maximum point. So on MySys is a stress value used to determine if a material, if a given material will yield or fracture, right? It's mostly used for ductile materials, such you've got sort of types of materials that you could use it on, and there's a yield that we have to look at and pay attention to here. And there's specific limits that we can work off. Sometimes it's elastic, upper limit, lower limit, and you get so forth, right? And if we look at the displacement side of it, we can see that the maximum displacement on this is just over 0.1 millimeters, so 0.13 millimeters. So it's fairly small displacement. Our maximum displacement that we could have went to was 0.55. So again, we way under that, meets design criteria, and we can work off it. Now, this is a nice way to actually analyze a little part that we're working on, which we know has small loads being applied to it and a little deformation that needs to go onto it. If we look at something a bit more different or a bit more complex, which takes a bit more longer sometimes to set up or to analyze, this is the non-linear stress. So if we look at the simulation type here, so it's a non-linear, displacement is large, and difference between linear and non-linear simulation. In linear analysis, the displacement starts at a tangential direction and remains in a tangential direction, as you can see in the display of the graph here, item number 1. So you can see it's tangential to the point of contact, or where the stress has been initialized, and moving down that plane. And in non-linear analysis, the beam cannot get longer with the axial load in the beam, so it displaces along an arc. So it's not a linear direction, right? If you're looking at figure number 2. If we go into it, so in this one, you see that simulation type again, material is not linear, right? Load direction changes as the model deforms. You can see plastic deformation on the graph on the side there. It goes from elastic and then it changes into a plastic deformation. So you can see where the non-linear factors come into play, right? At the yield strength, right? The displacement is fairly large. The direction of the load changes. Again, the strain curves deviates from a straight line, right? And materials have to contain a stress in the stress curve, as you can see that's happening there. Rubbery material or hyper-elastic materials. So hyper-elastic materials are a special type of material, special class of material, which tend to respond elastically, right, when they are subjected to large strains. So it's more like a rubbery-like kind of material that can withstand quite a bit of a large material, right? Large strain that's added to it. Hyperelastic materials, are regularly therefore large deformation when large deformation is required, right, within FEA. So when we use nonlinear simulation, anytime that you've lost displacement, right, we use a nonlinear displacement or nonlinear analysis. When stress exceeds the yield limit or strain of a region of the material, and also it'll never hurt the quality of the results to start a nonlinear simulation. It just takes a bit longer, right? For very short duration, non-static studies, an event simulation should be used, but that's something that we would discuss in future webinars, so not in today with event simulation. However, that is available to us in Fusion 360 as well. So the example that we're going to use here is the CV joint, the constant velocity joint. The material here, stainless steel. There's a bit of rubber, so non-linear, right, on it. The factors of safety that we're going to look at on the design criteria is 1.5. The stress is 75 megapascals, right, or just under that. If we go into this and get this going, you can see we'll do a section view of this to have a look and see what's happening in the model. We can obviously switch it off, go into our simulation environment, non-linear static stress, we choose that. And of course, material is first. We need to assign some material to this, generic. So we're going to go into Fusion non-linear material library, pick up the material required. So rubber in here. We can look at the properties as well. If they need to be reassigned, we can of course change them. We can look at the physical properties or the mechanical properties, the yield strength, the hyperelastic. There we go. We look at the curves. You can see the stretch ratio of them, right? at specific points, which is quite cool. Pick up the material again. Okay, constraints. So it's fixed at that point, and is a fixed point in there. Right. So we can just set up our structural constraint quickly. Our contacts. Okay. Automatic contacts there. And again, we can solve. Now, there's no need to go in mesh. We can do the cloud solving because it does the mesh when we do the solve itself. If we look at the results, we can see the safety factor is maximum 15, minimum 15 in it. We can look at the stress that's happening on it. If we look at the displacement, now what's quite cool here is we've got the little browser here that that allows us to actually slide the results through, so we could see what's happening. Now, if we look at the total displacement on this, the maximum is 1.197. So this meets design criteria based on the results that we looked at. If we look at it here, maximum displacement is 15, minimum is 1.165, right? So on our safety factor, sorry, on our stress, if we look at it, we can see what the maximum results is and what the safety factor is looking like. Now, if we look at it here, we can see that the safety factor is not great based on the results that we initially had. It was supposed to be 1.5, so resulting in maximum being good, minimum being also good. It is better than what the design criteria is, but it's just over it. But it's still fine for this design. So it meets design criteria. It's fine. We can move on with it. Now, if we look at factors of safety, just a quick overview on that. So again, the definition of this, factors of safety is a ratio that compares the allowable load or stress of a design with the actual applied load or stress. So from an FEA standpoint, this is typically defined as the equation that you see on screen. So factor of safety is equals to maximum stress over design stress, right? And there's an example of that. So where maximum stress can equal yield stress, optimal stress, shear stress, or even a fatigue-based stress limit is the maximum value your design should allow without any margin applied. Okay, design stress is the actual stress in your design when subject to the load case it is designed for. For the purpose of this case, the stress results given to us by our simulation. So basically, we can actually check what our safety factor is when we run the simulation, as we've seen, because it gives us the slider that we can look at, but also the tabs that we can change from stress to displacement to factor of safety as well, or safety factors. Okay, the typical safety factors can vary for different industries. So just some information for you to look at. So there's a broad range of safety factors that's used depending on where and what you're doing. So the aerospace, again, it's between 1.5 and 2. Pressure vessel design, 3.5 to 6, and lifting equipment between 4 and 10. As you can see, when it becomes more hazardous to close proximity working, you'll find that the safety factors get higher. That's not generally the case, but you'll find that being most common trend between that, right? And you'll see that the maximum stress should be determined by the application again. So depending where it is, it should be the application that is being used. That's where you'd find the maximum stress being used, and that's where the safety factors are determined, right? If we look at the load, static load cases typically used for yield or ultimate strengths, cyclic load causes may use endurance limits or other fatigue-based values. So depending on the material as well being used. So interpreting the results, right? So let's have a look at a bit of that. Are the results what I expected? What does the actual deformation look like? Where are the high stresses? So is there possibilities of singularities, so stress singularities? And what does the conversion plot look like? So if you look at some of the results and just having a look at it, the probes that you see on screen, maximum in green, shown as 15, and minimum shown as 0.4592. These probes are automatically there. You could also probe different areas of the model to see what's happening in that, and depending on what it is. So this is looking at safety factor here. For example, you see that we could actually drop the bar to see where are we, which areas are sitting between, let's for instance, 6 to 8, right? And we could see that, or in the minimum side, where are we sitting between 1 and 0? And we could move that bar around, and what it would do, it would show us where about in the model it is. Alternatively, we could probe the model, and the probe will tell us exactly what the safety factor is at the specific areas. If we look at the bar itself, there's multiple factors that we can look at. So the load case would be, of course, the one we look at on screen. But if we change that, you could see that you could choose from safety factors, stress, displacement, any strain, any reaction forces that's acting on it. So there's a variety you could choose from the radio button or the pick down drop list. And if we look at this in a bit more detail, you will find that there's also the slider that we could use. So for instance, like how we use that on the screen earlier on, where if it's on safety factor, you can move the slider to see where your maximum minimum is, which is quite nice. On the stress side of it, the Mises stress, you can see this first principle, third principle. You can look at the normal on the XX, YY, ZZ. You can look at shear as well on the different planes that's there as well. So depending on the results that you want to find or you want to look at, which gives you quite a nice comprehensive results with. Displacement also quite nice. There's different areas that you can look at the displacement. So you can look at the total displacement, X, Y, or Z axis. So that's quite nice. And what happens is, if we want to see where's displacement, what's the maximum displacement, of course our probes will tell us. But if we need to see it on the specific area of our model, we could actually choose X, Y, or Z plane and look at it. Now, another thing that comes to mind, which I thought I'll share with you, is the stress singularities. Now, stress singularities are things that appear when we run an FEA. Often what happens is it happens on areas that that come up on the model. So simplifying the model always helps sometimes. If there's a sharp curve or an edge or something that that causes the issue on one of the axes or on the planes, you get a stress singularity that comes up, right? So again, FEA theory uses the elasticity. So stress is equal to force over area, right? And no matter how much we define the mesh, so defining the mesh gives us often better results. But sometimes with the singularity, no matter how much we define the mesh, there's still a area that will remain zero, and this causes stress singularities, right? So these should be avoided because it could also sometimes, affect the results that we're getting in the long run. So the golden rule sometimes is that refining your mesh often enough. So generally start off with a bit of a coarse mesh, go finer, finer, and finer, and compare the results between the two, because the more accurate, the more finer your mesh, the more accurate your results generally is. All right, so that sort of brings us to more or less the end of the webinar. Just to give you, to recap on that, simulation, why do we use it? Again, it helps us validate our design before we do any physical prototype. So we'll be able to predict the what-if scenarios. We'll be able to see if the design can withstand a specific load. If there's a specific test that we need to do, we want to predict how it will function. Using simulation always helps us with that. And there's multiple types of simulations. As you see with Fusion itself, you can do various types, but if there's, you can take it further. There's also a simulation of fluids, where you can look at fluid flow, which is of course outside of Fusion, but that also forms part of simulation, where you can see how fluid flows through a specific type of material or into a specific pipe, or what is air doing, against something, often used in different industries. And also again in here, we've got the simulation for the stress side of it. There's also dynamic simulation to actually simulate moving parts. So there's multiple types. Today we just looked at the two, the linear static and non-linear. and the safety factors and how that works and what it does. So it is a bit of a introduction. I recommend that you go out, check it out, have a look at it. If you want to learn more, please log in or join the CADLearning. It's 100% Autodesk focused. There's lots of online tutorials, and there's over 50 different titles in here for Autodesk. There's Fusion inside of it. So if you want to get started with Fusion, you could go and access it here, and you could get access to Fusion and do some learning. And how do you get access? You can check it out on the Baker Baynes website. So if we look at www.bakerbaynes.com, you would see this CADLearning. You could get in, register yourself for a trial on CADLearning. If you like it, you can purchase it. Alternatively, you can get in contact with us via one of the methods on social media, or just info@Baker Baynes, just to get a bit more information on the CADLearning topics that's here, or if any questions regarding the presentation today. I'm going to jump into question and answers now. You can type in the chat box if there's anything that you want to, any questions that you have. We'll give it a couple of minutes, and yeah, we can take it from there. Just a quick one while the guys are typing in questions. Autodesk has an extended access program that includes Fusion 360. You could get an extended trial up until the end of May for it. So please, if you don't have access to it or you haven't used it before, please go and check it out. It's really, really nice. It's comprehensive design. You can get up to 5-axis machining or CAM on it, as well as the simulation environment, which we've discussed today. Is really cool animations and rendering functionality and capability on it, and it's a very lightweight program to work off. So if you haven't used it or checked it out before, I highly recommend that you go ahead and do so. Okay, so there's not many questions. See, there's one question here. Oh yes, okay. So the question here states, so what is the difference between the FEA environment in Inventor and Fusion 360? All right, so just to clarify, the simulation environment in Fusion 360 is powered by Nastran. So it's got the Nastran solver and does more, has more simulation capabilities than what there is in Inventor. And the reason for that is that Inventor has the standard FEA environment, which has been there for all these years, which is static stress and modal analysis that can be done in that. Inventor does have a dynamic simulation environment where you could actually have the parts move or simulated as it will move in real life, and that stresses from that can be taken into the FEA environment. However, it is limited when it comes to that. If you have a collection, though, you could use the Nastran, so Nastran NCAD, and it'll give you the same capabilities that you've got in Fusion 360 to run these simulations that you need. So it does have the same if you're using the full collection, but if you're just using Inventor itself, Inventor Professional that is, then you've only got access to the static analysis and the model analysis that's there. All right, no more questions. Please feel free to get in touch with us if you have any questions afterward or something has come to mind. Please get in contact. You can contact us at info@Baker Baynes, or alternatively, you could get in touch with us via one of our social media platforms on screen. So LinkedIn, you could find us on LinkedIn, Facebook, Twitter as well, Instagram, or also check out our YouTube channel for past webinars that's been there. It's really great content, good learning, especially at this time where everyone is working remotely and working from home. It's very nice to actually get in contact with us to see how we can help you work remotely, or if there's any questions that you might want to have, CADLearning, for instance, definitely get in contact and we'll be able to help you out. Thank you for joining and attending the webinar today. If there's any questions, please follow up and let us know after following the webinar. Please let us know, and have a great Friday.